So in chemistry, thermodynamics, which is enthalpy and other terms that we'll look at more later, are useful because they can tell if a reaction will be product or reactant favored. Product favored means the reaction will occur, and reactant favored means the reaction will probably not occur. But it doesn't give us any information as to how fast the reaction goes from reactants to products. And again, if a reaction is going to take millions of years, who cares if it's going to go or not, because that's way past our lifetime, if you know what I'm saying. So kinetics is the study of how fast reactions go. A rate is essentially a speed when it comes to chemistry. So reaction rates are basically the speeds of reaction. And we're going to see how to make the reaction go faster and slower. And along the way, we'll also learn about how reactants go to products. And that's through something called the mechanism. Up to this point, we have only looked at reactants and products, the beginning and the ending. But have you ever wondered what happens in the middle? That's where a mechanism becomes really helpful. A mechanism will allow us to investigate the path, if you will, that reactants go to products in order to have that happen. And it's really fascinating. We'll see some really interesting kind of chemistry along the way. So anyway, it's kind of cool. We're going to see what happens between the reactants and products. We're going to see what happens within the arrow between the reactants and products. It's a pretty cool chapter. Now, the speed, as I said earlier, of a reaction is called a reaction rate. So every time you hear rate, just think speed. And speed is no big deal if you're, say, driving a car or something like that. You know how many miles per hour you're going, or kilometers per hour if you're in Canada. A reaction rate will be similar. It's the speed of a chemical reaction. And the rate of reaction is just, again, telling you how fast it's going to go from reactants to products. And this is going to be part of the tool we'll need to control the chemical reaction to figure out what makes it go fast and what makes it go slow. So a rate is going to be, for chemistry, how much of a quantity of reactant or product changes over a given amount of time. And again, the speed of a car is usually how many miles are driven per hour, something like that. That's how speed is expressed. So units of your car will be miles per hour, kilometers per hour if you're in a metric country, stuff like that. In chemistry, though, we don't have miles to travel, or kilometers for that matter, but what we do have is moles per liter used per second. It's quantity used per unit time. And so usually the time is in seconds, and usually the speed is listed in moles per liter per second. All right. Molarity is the number one unit when it comes to chemistry. It's used more than anything else. And so most of the time, the rates, the speeds, are listed in how many moles per liter are being used per second. So if you see something like you do there in the lower right-hand side, where it says rate equals minus delta H2 over delta T. Let's look at that a little bit. So first of all, things in square brackets, like the H2, that's moles per liter, all right? So that would be saying the moles per liter of H2. And then delta, like we've seen before, delta is final minus initial. So if the final time is T2 and the initial time is T1, then delta H2 will be the change of the H2 concentration at time 2 minus the H2 concentration at time 1. And likewise, delta little t on the bottom will be delta time. So it'll be the time at time 2 minus the time at time 1. So anyway, this will all make sense here in a little bit. It's a little bit weird, but that's what it means. Just remember delta, final minus initial. And then if you see things in square brackets, that means moles per liter. A chemical reaction, the speed of a chemical reaction, is a little different than your car, all right? Because you have to know how the concentration of the reactant is decreasing, because reactants are used up. But sometimes you can also think about how much product is appearing, because products appear in a given reaction. So when you write something like we did for that H2 thing on the bottom, if it's a reactant, we need to put a negative sign in front of it. And this is a little strange, but let me try and explain to you. H2, if it's a reactant, its concentration will constantly be going down, because in any chemical reaction, reactants are used up and products are created. So the change in H2, the final time where H2 is measured minus the initial time where H2 is present, that's going to be a negative number, all right? So the delta H2, delta for any reactant is going to be a negative number. So scientists put a negative in front of reactants to make those negative signs cancel out, and you end up with a positive rate. So number one thing to learn so far in this chapter is that when you're talking about the speed of a reactant, you need to put a negative sign in front of it because the delta reactant concentration is a negative number, and negative times negative makes it positive, which everybody likes. So anyway, just realize that if you have a speed of a reactant, all right, you need to put a negative in front to make those negative signs cancel out. So this H2 plus I2 making 2HI is a great example of how scientists need to think about speed. Now, if you have a car, there's like only one speed, the speed of the car. But in chemistry, it would be nice to think about the speeds of reactants, how fast they're disappearing, and also the speeds of products, how fast they're appearing. And in order to make the negative of the reactants go away, we put a negative sign in front of those, like we talked about. But there's another thing that you have to think about as a chemist, because for every one H2 that's being used up, you're going to make 2 HI. So that stoichiometry, that 1 to 2 ratio is also important. So if you use up 1 mole of H2, you're going to make 2 moles of HI. And if you use up 2 moles of H2, you're going to use up 4 moles of HI, etc., etc. So chemists also have to deal with the stoichiometry of each chemical in the speed. So, this is a little weird, but bear with me here. If you're going to talk about the speed of a reaction, it's nice to think about the speed in terms of both the reactants and the products. But there are two things you need to do. And if you look down there at the bottom, this is a great example. We have some kind of random A reacting with some kind of random B, and that makes big C and big D on the right. But also notice there's the little a, little b, little c, etc. Those are the stoichiometric coefficients. Now, in order to make the speed of the reactants be equal, make sense to a speed of a product, there's two things you need to do. And number one, we've already talked about. You need to put a negative sign in front of the reactants. So big A and big B are reactants, and they both have a negative. You'll see in front of C and D, there's a positive sign. You don't change those because the change of a product will always be positive. The change of a reactant will always be negative. So that's the first thing. But the other thing you need to do is you need to go 1 over the coefficient for any reactant or any product. So you can see that all those things down there have a 1 over little a or 1 over little b, 1 over c, etc. That's just to make all of the speeds the same, because HI in the H2 plus I2 making 2 HI reaction, that's appearing twice as fast as the H2 and the I2. So the speed of HI appearing would be twice as fast, if you will, as the H2 disappearing. So you put 1 over the stoichiometric coefficient in front of it, and those will all be taken care of. Now, if everything I've just said in the last minute or so is gobbledygook, and I understand, here's the punchline. Number one, when you're talking about the rate, if it's a reactant, put a negative sign in front of it, and if it's products, then you just put a positive sign in front of it. But number two, the other important thing is that you always want to have 1 over the stoichiometry in front of the chemical. So the balanced reaction will tell you the stoichiometry. If it's just a 1, of course you can ignore it, but if it happens to be a 2, then it would be 1 over 2, or 1 over 3 if the stoichiometry is 3, stuff like that. So let's look at an example of how you can figure out the expression for a rate in chemistry. And remember, what we're doing here is we're figuring out the speed, but we're trying to relate a speed which makes sense for reactants to a speed that makes sense for a product. And so along that way, what we're going to do in this problem is we're going to talk about average rate and the individual rates. So what we have here is a reaction where hydrogen peroxide is reacting with iodide, I minus, and some acid, H plus. And it makes what's called the triiodide ion, I3 minus, and some water. But here's the important part. In the first 10 seconds of the reaction, the concentration of the iodide dropped from 1 molar down to 0.868 moles per liter. And we can use that information to calculate the average rate of this reaction during this time interval. We're also then going to take that average rate and we're going to figure out the rate of change of concentration of the H+, i.e. we're going to find a specific rate, a specific speed for another chemical, another reactant, which is H+ during this interval. Okay, so first of all, the average rate, we're going to use that expression up there in the upper right. And because this is a reactant, iodide, I- is a reactant, we'll use one of the left-hand ones. So notice therefore the rate of the little a, it's -1 over a, change of the delta A in moles per liter divided by delta T. And we're going to do something like that for iodide. Now again, because iodide is a reactant, we have to put a negative sign in front of it. And the other thing that's important here, there's a big 3 in front of the iodide in the reactant chemical equation. So we're going to have a 1 over 3 in front of that to make sense. So initially, the rate is going to equal -1 over 3, the delta I- concentration over delta T. And again, iodide is a reactant, so that's why the negative is there. And there's a 3 in front of the iodide, so 1 over 3 is what we'll put there. And then the rest of it is delta I- over delta T. If this would have been a product, we would not have used a negative sign. It would have been just positive. But either way, whatever the stoichiometry is, those big numbers in front of the chemicals, you want to put that in front of it. Now, delta, as I said, is final minus initial. And we're going to do final minus initial for the iodide concentration. That's going to be the final concentration 0.868 and the initial concentration 1.000. And the delta time, the final time will be 10 seconds, and the initial time will be 0 seconds. So if you throw all of that in your calculator, you get a speed for the iodide of 4.40 times 10 to the -3 molar per second. Now, notice that the 0.868 minus 1, that would have been a negative number. Reactant concentrations are always going down. So final minus initial will always give you a negative number. And that's why I've been hyping so hard that if it's a reactant, put a negative sign in front of it. The negative sign will neutralize the reactant concentration values, which are negative, and make it an overall positive speed. So the average rate for this chemical reaction, 4.40 times 10 to the -3 molar per second. So every second, this reaction is using up 4.40 times 10 to the -3 moles per liter. That's what it's saying. Now, in the second part of this reaction, we're going to do delta H+ over delta T, and it's going to look somewhat similar. The H+ has a 2 in front of it, so instead of 1 over 3 like we had for iodide, we're going to use 1 over 2, and H+ is a reactant, so there'll be a negative in front of it. So the rate for this one, rate will be -1 over 2 delta H+ over delta T. So again, notice it's a reactant, so we put a negative in front of it. It's 1 over 2 this time because H+ has a 2 in front of it, not the 3 like we had last time. So this is what we have. Now the rate, the expression on the left, that's 4.40 times 10 to the -3. So we're going to rearrange this expression for delta H+ over delta T. So if you do that, you get -2 times the previous rate, -2 times 4.40 times 10 to the -3, and that comes out to be -8.80 times 10 to the -3 molar per second. Now, while 4.40 times 10 to the -3 molar per second, answer A, that's the speed of the overall reaction. It can be used for reactants and products, but that's the overall speed. The -8.80 times 10 to the -3 number we just calculated, that's the speed for the H+ disappearing, essentially. It's how fast the H+ is disappearing. So reactant concentrations are always going to be negative, so the speed of the reactants by themselves will always be negative, like the 8.80 times 10 to the -3. However, the overall overall rate and the rate of the product, if you want to figure that out, those numbers will always be positive. So it's a little strange, but it's nothing you can't handle. And again, if you have questions on this, reach out to me or reach out to the Learning Success Center / Avid Center, and they can help out as well. This is a graph showing N2O5 decomposing, and there's actually different kinds of rates that are possible. And if you had calculus under your belt, or maybe you have calculus under your belt, integration and differentiation are really great tools to have for figuring out rates. But you don't have to have calculus under your belt, certainly for Chemistry 222. So what we're going to do in this class is just talk about average rate, all right? And the average rate is just the easiest way. You just use it as an overall speed for the overall reaction. It's good to go. But if you study kinetics more in the future, you might see some of these other kinds. They can be pretty powerful. So here's a question. It says, what's the average rate of this reaction over the first 2 minutes? Okay. And you can see here there's different concentrations on the y-axis, and the time is on the x-axis. So the first 2 minutes then, you can see on the x-axis, there's a 2 right there and a 0 right there. So if you go up to where the 2-minute part is, it's right there. And if you go up to where the 0 time is, it's right there. So what we're going to do here, rate is going to be the average change in the concentration over time. Now this is a reactant. Notice how those numbers are getting smaller as time goes on. So the reactants, we always put a negative in front of them. We're going to assume the stoichiometry is 1 since we have no better idea. So the rate will be a negative for the reactant, and then it'll be the change in the reactant at 2 minutes minus 0 minutes. So for this problem, it looks like that's going to be roughly at 2 minutes, roughly 1.7, and roughly at 0 minutes, roughly 3.4. So it'll be 1.7 minus 3.4 or something like that. And then in the denominator, you'll have the change in time. So that'll be 2 minutes minus 0 minutes. It'll be 2 minutes. So if you calculate this then, you'll have negative for the reactant, 1.7 minus 3.4. Those are the numbers for the concentration at 2 minutes and 0 minutes. And then on the denominator, you'll have 2 minus 0. That's delta t, delta time for the time elapsed. 2 minus 0, throw that out on your calculator, 0.85 molar per minute is the speed. The average rate will always be a positive number. Having a negative number would be like turning products into reactants, and that's a little advanced, shall we say, for this course. But in our class anyway, the overall average rate will always be a positive number, but you can see how this is. So you can use a graph to figure out the concentration values, divide them by the time values. Good to go. This is a trick that can be handy, and it's an approximate time elapsed for a reaction. And this isn't always totally right, but it gives you an idea. So remember that all the rates that we've seen so far have been some kind of moles per liter per unit time, usually per second, all right? Well, if you have a rate and you have an amount of compound that you start with, you can solve for time here and figure out approximately how much it's going to be. So as an example of this, 4.3 times 10 to the minus 6, we'll say that's the speed, the molar per second. And the amount of compound we're starting with here is 0.00250 molar. It would be nice to know approximately how long it's going to take to react. So if rate equals concentration A over time, let's solve for time. Time's going to be concentration divided by the rate. And if you do that and you throw those numbers in there, so you can see on top is the amount of the reactant we started with divided by the speed that it's going, it should take roughly 580 seconds for it to complete. Now, I have used this to high success sometimes in some of my research I did back in my graduate school days. I had some reactions that would take hours and hours to go, and I didn't want to sit there and wait there, so I would figure out an approximate amount of time for them to happen. I would then go and do other things, go to the library or do whatever, go to a movie, who knows. But anyway, they took a long time to go. But anyway, they gave me a rough guide. And, if it says it's going to take 580 seconds, you want to start watching about 500 seconds in case the sig fig rules are weird or something. But it does give you a rough idea as to how long a reaction will take to happen.